Welcome back. This is College Algebra. This is the lecture on section 2.3, functions. Okay, so to start off, first of all, we've got something called a relation, which is just a set of ordered pairs. It's just some grouping of them. Right? So we saw ordered pairs last time. We could plot these on a graph. We've got our x and our y coordinate, right? Now, a function is a special type of relation in which each x value corresponds to exactly one y value. Okay, so if you look at the green relation, we've got the x value 1 appearing 3 times, and each time it's going with a different y value. So that's not going to be a function. A function is going to be where each x value is going with its own y value, right? Just a single y value. So we have a single input and a single output, not one input and 3 possible outputs. Okay. And note that it's fine that 2 different x values can give you the same y value. Okay, so different inputs can give you the same output, but the same input should give you a single output. Okay, so we'll see how this works as we go on a little bit more, but this is just a little bit more of a visualization. If we listed out the x values, 1, -2, and 3, we can see how they map to our y values, 2 and 4. So we can have 2 different arrows going to the same place, but we shouldn't have, from our x values, one number going to 3 different places or something like that. Okay. So let's see. Let's determine whether the following relations are functions. We've got A, which is 1, 1, 2, 2, 2, 3, and 3, 4. You've got B, 1, 2, 1, 1, 2, 1, 3, 1, and 4, 1. Okay, so this relation B, all of them have the same y value. So if we do our mapping, we can see that in A, the x values, well, 1 is going to 1, but 2 is going to 2 different places. It's going to the y values of 2 and 3. And 3 is only going to 4. But this right here, this is a problem, right? So 2 is corresponding to more than one y value at once. Therefore, this is not a function. It's just a relation. Okay. On the other hand, B, if we list out our x values, we've got 1, 2, 3, 4. All of the y values are the same. They're all going to the same place. But that's fine, because each x value is not corresponding to more than one y value. Therefore, this works. This is a function. Okay. So again, every x value has to just go to one y value. Every y value can have multiple x values coming to it, but that doesn't matter. That doesn't stop it from being a function. Okay. Next, let's talk about domain and range. Domain is simply the set of all of the x values, or the inputs, as I've been calling them. Range is going to be the set of all of your y values, the outputs, what's coming out of this, as we're going to talk about function. Okay. So let's look at example 2. Give the domain and range of each relation. Determine then if it is a function. So we've got C and D here. All right, well, C's domain is going to be the list of all of its x values. So we've got 3, 4, 4 again, but we don't need to list a second time. We can just list it once. And then we've got 6. Okay, so 3, 4, and 6. Its range is just going to be the list of all of its y values. -1, 2, 5, and 8. And that's what we've listed here. Now, this is not a function because 4 is paired with 2 different y values, right? So if we were to draw our little mapping, we'd see that we've got 2 different arrows coming out of 4. They should not be going to different places. Therefore, this is just a relation and not a function. Then we've got these. So we've got 4, 6, 7, and -3 as our domain. And our range is just going to be 100 and 200. So 200 is appearing 3 times. We just need to list it once. Now this is a function because each x value corresponds to exactly one y value. For each input, you're only getting a single output. Here we had a single input 4, but we could get 2 possible outputs, which prevents that from being a function. All right, example 3. Now let's see if we can determine domain and range from the following graphs. So we're talking about how these functions are just groups or sets of ordered pairs. So we can plot these and we can go ahead and take a look at these graphs. All right, well, we've got all of these points out here. The domain is just going to be whatever x values are covered by these points. Okay, so if we listed these points out, the first point is going to be 2, 2. The second point is going to be 4, 3. Then 6, 1, and finally 9, 6. So our x values are going to be 2, 4, 6, and 9. Our range is going to be the collection of all the y values, which is simply going to be 2, 3, 1, and 6. We can just list them from least to greatest, 1, 2, 3, 6. Okay, it doesn't matter. They're the same thing, but this is the convention. So our range is going to be 1, 2, 3, 6. Now those were for what we call discrete points or separated points. What if we had a full-on line? And as we'll see in a second, a curve. So all of these points are connected. We have infinitely many points here. So now we're not going to be listing them out in the same manner as a list of ordered pairs. Now we're just going to see, what range, or I should say, what interval of x does the domain span, and what interval of y does the range span. Okay, so our domain, well, we're running all the way to the left over here out to negative infinity, and we're running all the way to the right here up to positive infinity. So our domain is simply going to be negative infinity to positive infinity, or all real numbers. And the same thing's true for our y. This graph is going down. It's just going to keep lowering all the way down to negative infinity in this direction, and it's just going to keep going up and to the right into that direction, which is positive infinity. So it's the same thing. So both the domain and range are going to be all real numbers. They're going to run from negative infinity to positive infinity. And then for example C, well, we've got a curve here, but unlike before, we don't have these arrows out here, right? So we've got a point here and a point here. So we do have endpoints this time. So we're not going to be running from negative infinity to positive infinity. Instead, our domain, well, our x values are running from negative 9 up to 8. But it does cover everything else in between, okay? So we can still give this as an interval. So we're including negative 9, and we're including 8. So written in interval notation, this will be with brackets from negative 9 to 8. Or you can say x is going to be greater than or equal to negative 9 and less than or equal to 8 simultaneously. Okay. The same thing is true for the range. We're starting here with the y value of 1, and the highest this is going to go up to is 5. Kind of drew a little bit above 5, but that's supposed to be 5 up there. Okay, so the same thing from 1 to 5 with brackets because we are including those values. All right, so we can also see domain and range from a graph. Next, we've got something called the vertical line test. Now, this is going to help us figure out if a graph is a function or a relation. So we don't always need to think about how the x values are mapping onto the y values by looking at the points. We can actually just draw a vertical line through this graph. And what we want to see is, how does this vertical line intersect the graph? So if it intersects with the graph exactly once, that graph is a function. If it intersects the graph more than once, it's not going to be a function. And this is going to happen because for the same x value, if we have two different y values, well, they're going to be right over each other, right? So I think earlier we saw an example where we had something like 4, 2 and 4, 5. These 2 points are going to be right on top of each other. And if we drew a vertical line, we'd be intersecting more than once. Okay. So here in example 4, I've got a parabola here in green. If I draw that vertical line through it, at any point really, I see that's only intersecting once. It's passing the test, and therefore this is a function. In example B, well, now I've got this same shape, but it's kind of facing sideways now. And now if I draw a vertical line, we're intersecting up here and down here. We're intersecting twice. This is going to fail the vertical line test, and therefore this relation is not a function. Okay. So the vertical line test is just a quick way to visualize what we've already been talking about in terms of the y values and the x values. Next, let's see if we can figure out functions, their domains and ranges just from looking at the equation. So we've got y equals x plus 5, first of all, to start off with. The first question is this a function? Well, y is always going to be found by just adding 5 to x. So for every x value that we put, we're just going to get a single y value. It's just going to be 5 more than that. If we put in 0, we're going to get 5. If we put in 1, we're going to get 6. If we put in 2, we're going to get 7, so on and so forth. So every value of x is just going to be corresponding to one value of y. Therefore, this is a function. Now, as far as domain and range are concerned, for domain, it doesn't appear that there's any sort of restriction. I can just plug in any x value. I don't have to worry about square roots or a denominator becoming 0 or anything like that. So I can just plug in any x value or any number for x. And that means our domain is going to span from negative infinity to positive infinity. And if that's true, well, if I can just plug in any number for x and I'm just adding 5 to it, then our range is going to be the same thing. It's just going to be 5 more than x, so it's also always going to be a real number, and it can be anywhere in the span of negative infinity to positive infinity. Okay, that's example A. Now let's look at example B. We've got y is equal to the square root of 2x minus 1. So now we've got a square root going on here. The inside of this, for any radical, has to be greater than or equal to 0. We cannot have a negative inside of a square root. Okay, so that's an important stipulation we'll have to consider. But the first point is that for any choice of x in the domain, there's exactly one value of y that corresponds to it, right? So the same thing happens. We're going to do this operation, and we're only going to get a single value of y for whatever we put in for x. Therefore, it is still a function. Now let's think of the domain. Because the square root, the quantity under the radical, cannot be negative, just like we're saying. So let's make sure it's not. So let's set up an inequality for ourselves. 2x minus 1 inside the square root has to be greater than or equal to 0. If we solve for x, so first we add 1 to both sides, divide both sides by 2, we're going to see that x has to be greater than or equal to 1/2. Okay, so only those x values which are greater than or equal to 1/2 are allowed. Those are the only x values you can plug into here and make this work. So that means our domain has to now start at 1/2. So we're going to include 1/2, because if we plug in 1/2, we'll get 0. That's fine. So we're going to get from 1/2 all the way up to positive infinity. The range then is going to be, well, from 0 to positive infinity. 0 is going to come about because that's the value of y when we plug in 1/2 for x. And as we plug in higher and higher numbers for x, they're just going to increase to positive infinity as well. So our range is going to be 0 to infinity. Okay. Next, we're going to talk about function notation. So now we can express functions as y is equal to f of x, is how we read this, right? So f of x, f parentheses x, this means the value of f at x. Okay, this is not saying f times x. I know we've seen, before something like 2 times x plus 5 when they're just written next to each other, something like that. No, but this, for function notation, this is saying that we're inputting x into some sort of function, and that's going to give us the output y. Okay. So for example, let f of x equal 3x minus 5. We might be asked to find f of 2. So we're going to evaluate this function when x is equal to 2. Okay, and that's exactly what it means. The value of f at 2. So you plug 2 into your function. 3 times 2 minus 5, 6 minus 5 is 1. So f of 2 is simply equal to 1. And this corresponds to, right, just like we said before, well, y is equal to f of x. So that means your y value here is 1, and your x value here is 2. So 2 comma 1. Okay, so we've got example 6 here. Now they're saying let f of x equal negative x squared plus 5x minus 3. Let g of x equal 2x plus 3. And we have to find these values. So first find f of 2, find g of 8, and then find f of q. And then we've got a part D as well. Find g of a plus 1. Okay, so you can take a moment to try those on your own, and then we'll go over them. All right, let's take a look at the solutions. So for part A, we're evaluating f of 2, so we are going to plug in 2 in for x. Okay, wherever we see it, we're going to put in 2, and we're going to make sure we put these in parentheses, especially when we start substituting more than one term. We want to make sure if there's some sort of coefficient or negative sign, that we're going to distribute that across our parentheses. So here we just have a 2. We're going to follow our order of operations. We're going to square that 2 first. We'll get 4. And then we're going to put that negative in front of it afterwards. Here we just have to multiply 5 times 2. We're going to get 10. Negative 4 plus 10 minus 3. We put that together. We get 3. Okay, so in this case, f of 2, the function f evaluated at x equals 2, is 3. And this is going to correspond to that point, 2 comma 3, okay, if we have to plot this. Next, we've got g of 8. So in here for x, we're just simply plugging in 8. We're going to get 2 times 8 plus 3. 16 plus 3 is 19. Now C says, find f of q. So this time they're not giving us a number. The only thing we have is this variable q. So all we have to do is, wherever we see an x, just replace that with q. That's it. Okay, so a function can be evaluated at some other variable instead of f of x. Now it's f of q. And finally, for part D, we've got find g of a plus 1. Okay, so now we are plugging in multiple terms wherever we had x before. So we're going to make sure we do this in parentheses. So we have 2 times in parentheses a plus 1 plus 3. We distribute that 2 across the parentheses. We get 2a plus 2 plus 3, which simplifies to 2a plus 5. Okay, next we've got example 7. Part A says rewrite the following as a function of x. So we've got x minus 4y is equal to 5. We're going to try to isolate the y, rewrite y in terms of x, and then we can replace y as a function of x, so f of x. And then finally, we're going to use that to find f of 8. So let's see how that looks. So we've got x minus 4y is equal to 5. We'd like to isolate y, so we're going to subtract x from both sides. Negative 4y is equal to negative x plus 5. Our last step here is going to be to divide both sides by negative 4. So negative x divided by negative 4 is the same thing as positive 1/4. Positive 5 divided by negative 4, we can just leave that as negative 5/4. So we've isolated y, and now we're just going to replace that y with f of x. Okay, so this is our function f of x. Now to find f of 8, we simply need to replace x with 8. So we go ahead, we plug in 8, 1/4 times 8 minus 5/4. I'm going to leave that as 8/4 because we have to subtract 5/4 from it. Otherwise, we could just simply reduce that to 2, but we want to keep that common denominator. So 8/4 minus 5/4 comes out to 3/4. And now for the last topic, we're going to talk about increasing, decreasing, and constant functions. Now, a function can also be increasing and decreasing on different intervals, and it can even be constant on a different interval. Okay. So let's see how this works. So f is increasing on an interval if whenever x1 is less than x2, f of x1 is less than f of x2. So all this is saying is when we're going from left to right, so x1 is less than x2, the y value that goes with x1 is less than the y value that goes with x2. So as we go from left to right, our function is going up. And that's the definition of increasing. F is decreasing on an interval if whenever x1 is again less than x2, so we're going from left to right. This time the f of x1 value is greater than the f of x2 value. So the y value that goes with x1 is greater than the y value that goes with x2. So as you move from left to right, your function is going down. It's decreasing. And finally, f is going to be constant on an interval if whenever x1 is less than x2, again, when we go left to right, f of x1 is equal to f of x2. So their y values are staying the same as we go from left to right. And that's the definition of a constant function, or a function being constant on some interval. All right, so example 8 says, find the intervals on which f is increasing, decreasing, or constant. So let's take a look at this graph. Okay, so we've got a little bit of a V shape here, and then our function becomes a horizontal line. So again, so we're looking from left to right. When our y values are dropping from left to right, that is our interval of decrease. So in this case, from 1 to 5. When we are going from left to right and our y values are increasing, that's going to be our interval of increase. And of course, when our y values are staying the same as we go from left to right, we are constant. Okay. So this is with those colors here. Now, this function is, I guess, defined from, it's drawn here from 2 to 5, but we can assume that this is going out to negative infinity on the left side. So it's decreasing from the interval from negative infinity up to 5. Now, you can see we put a parentheses here. We're not going to include the 5 because the 5 is also the point where you could say it starts increasing, right? So this is one of those like turnover points. So we don't include these in our intervals. So we're going to say it's decreasing up to, but not including 5, or for x is less than 5. So similarly, it's going to be increasing from 5 out to 9. And we're not, again, including either the 5 or the 9. So this is when x is between 5 and 9. And the same thing is going to be true for constant. We're not going to include that 9, that turnover point. We're just going to say from 9 to infinity, or x is greater than 9. All right, so this was a quick look at functions. I hope this helped lay some groundwork that we're going to build on for our future lectures. Thank you for watching. If you enjoyed this video, please like and consider subscribing to the channel for more content like this.